Welcome to Let's Get to the Marks, going through an A-level chemistry AQA revision pack from the Physics and Maths Tutor website. This one's on Equilibrium. Big shout out to the members, Nicola Korzik and Ashford, for supporting the channel. Thank you very much. Let's get into it. Let's go. Don't forget to pause the video, have a go at the question with some scrap paper, and then unpause and check off your answer. Hydrogen can be prepared on an industrial scale with a reversible reaction between methane and steam that we've got here, shown here. It's endothermic, plus 206 kilojoule per mole. The reaction is done at a temperature of 800 degrees, a low pressure of 300 kilopascals in the presence of a nickel catalyst. Explain in terms of equilibrium, yield and cost why these conditions are used. So this is really broken down into three parts with two things to say about each of the three parts, and that's going to get you your 6 marks. So we need to talk about why it's done at 800 degrees, then why it's using a low pressure, and then catalyst. So you can put it into temperature, pressure, catalyst, and we need to, for each of those three things, consider yield and cost. And if you can do that, that's going to get you 6 fat marks. So first of all, the reaction is endothermic. You can tell that because it gives out plus 206 kilojoule per mole to the -1. That means it's endothermic on the right hand side. So if we use a high temperature, remember Le Chatelier's principle says that the reversible reaction in a closed system will try and oppose that change. So what that's going to do, a high temperature shifts the equilibrium to the right hand side, to the endothermic side, because it's going to try and reduce the temperature. And how are you going to do that? You're going to move to the endothermic side, the side that takes in heat. So yeah, high temperature, good stuff. We're going to get a high yield because it's going to shift the equilibrium position to the right, giving us a higher yield. However, now we need to consider the cost aspect. High temperatures cost, so 800 degrees is a compromise. Like, why not use 1500 or double that, 1600 degrees? Well, because we also have to consider cost, and the higher the temperature, the higher the cost. Now we could actually link into the third point, which is the nickel catalyst, because actually if you use a nickel catalyst, you lower the activation energy, which also helps you not have to use such a high temperature to make that compromise, because lower activation energy, you don't need such a high temperature, so you're going to save on money. However, the catalyst has no effect on the equilibrium position. We need to mention that catalysts do not affect the equilibrium position. They won't directly affect the yield, but they will lower the activation energy, which will reduce cost, and it will actually increase the rate of reaction. Okay, now let's consider the pressure situation for our third thing. So you could have done this in any order. I mean, you might have felt the natural order was to do temperature, pressure, and then catalyst, as that's the order they put in the stem of the question. But a low pressure of 300 kilopascals is used as the reaction will shift the equilibrium. Remember, it's trying to oppose the change. If you use a low pressure, it will shift the equilibrium to the side with the highest gas molecules, and that's the right hand side again, which will increase the yield. And why is it going to shift that way? Because there are 4 gas molecules on the right compared to 2 on the left. So if you reduce the pressure or use a low pressure, it will try and oppose that low pressure by moving to the side with the most gas molecules, which is the right hand side. Again, this actually helps because low pressure doesn't cost as much as high pressure. High pressure, you need thick steel vessel walls for your vats and your containers for your chemicals to prevent explosions. You'll need safety equipment, all of that kind of stuff. So high pressure is very expensive. So again, this is a cost saving by using a low pressure, and it gives us a high yield because it shifts to the right because there are the fewer gas molecules on the right. That's your 6 marks. Bish, bash, bosh. Right, question 2. Okay, zooming in for a closer look. Question 2. Which statement about the use of a catalyst in a reversible reaction is correct? So which of these is true? The activation energy for the reverse reaction is increased. The equilibrium constant increases. The rate of the reverse reaction increases. The enthalpy change for the forward um, reaction decreases. Well, the equilibrium constant increases. No, catalysts do not affect Kc. They don't affect the equilibrium constant. They don't change the position of equilibrium. Let's look. The rate of the reverse reaction increases. That's true. the rate of both reactions increase. The forward reaction and the backwards reaction increase, and the activation energy lowers. The enthalpy change for the forward reaction decreases. Catalysts don't decrease the rate of reaction, and the activation energy is increased. They don't increase activation energy, they always lower activation energy, don't they? So it's definitely C. The rate of the reverse reaction increases, but also the rate of the forward reaction increases, right? You might say, well, how can it lower the activation energy for what lowers the activation energy for both reactions, for both directions, the catalyst? So it actually means you reach equilibrium faster, although it doesn't affect the equilibrium position. It increases the rate of reaction, so you're going to get to equilibrium faster in a sealed container, but it will not change the position of equilibrium, and therefore it will not affect Kc. All right, let's move on.
Keep moving on, keep moving on, keep moving on, keep moving.
Question 3. This is about equilibrium. We've got 2 sulfur dioxides plus 1 oxygen molecule, reversible sign, go to 2 sulfur trioxide molecules. State and explain the effect, if any, of a decrease in the overall pressure on the equilibrium yield of sulfur trioxide. So we're going to get a mark for stating the effect and 2 marks for the explanation here. Let's look at the number of gas molecules, I can't spell, oh my gosh, number, on each side. So I've got 2 sulfur trioxides plus an oxygen, that's 3 on the left, and I've got 2 sulfur trioxides on the right, so that's 2 on the right. So I've got 3 and 2. So what's the effect if we decrease the pressure on the yield of sulfur trioxide? Well, Le Chatelier says that the reversible reaction will try and oppose the change. If we decrease the pressure, it will move to the side with the most gas molecules to try and increase the gas pressure again. And so this is going to shift the equilibrium to the left-hand side, and we're going to get a decrease in yield. So really the effect is to reduce the yield, and the explanation is shifts to the left, 1 mark, trying to oppose the change, goes to the side with the most gas molecules. So it's Le Chatelier's principle when the reversible reaction in a closed system will try and oppose a change, and it will always shift to the side. If you're decreasing the pressure, it will always go to whichever side has the most gas molecules in order to try and increase the pressure back and oppose the change to counter the condition you've changed. And that will get you 3 marks. So the main key points amongst all this waffle is reduce the yield for the first mark, and then shifts the equilibrium to the left because it has more gas molecules. And that is all you really needed to write. Right, part B, we've got a calculation. Calculators at the ready. 0.460 mole sample of sulfur dioxide is mixed with a 0.250 mole sample of oxygen in a sealed container at constant pressure. When equilibrium is reached at a pressure of 215 kPa, the mixture contains 0.18 mole of sulfur trioxide. Calculate the partial pressure in kPa of sulfur dioxide in the equilibrium mixture. I'm going to draw an ice table so I can work out how much, what is the total moles at equilibrium. Okay, that's what I need to know. So I have, let me write the equation out again. Sulfur dioxide, what was it? Plus oxygen goes to sulfur trioxide. And I had 2 moles of sulfur trioxide, and there were 2 moles of sulfur dioxide, right? And 1 mole of oxygen. Okay, we need the ratios so we can work out the number of moles. Now let's put our initial moles. We had 0.460 of sulfur dioxide. This is the initial moles. And of oxygen, what did we have? 0.250 moles of oxygen. So you write this little ice table out. And then there's going to be 0 moles of sulfur trioxide initially because the reaction started. You put your reactants together. You can't have any product. So 0 for that. Now we want to work out the change. It says at equilibrium we had 0.180 moles of sulfur trioxide. So we're going to write that down, 0.180. And that means it changed. That's what the C in the I stands for, by 0.180. We now look at the ratio and work out the change for oxygen and sulfur trioxide. So the ratio of sulfur trioxide to the oxygen is like 2 to 1. So what I want to do is divide 0.180 by 2. Use a calculator just to double check, because you might slip up like I did there. I started to write 0.9, like 18 divided by 2 is 9. Of course, it's 0.09 when you divide 0.18 by 2. And then it's a 1-to-1 reaction with sulfur dioxide, so that means that's going to change by 0.180. So now we just need to take the initial moles, take away the change, and get our equilibrium moles. So 0.460 minus 0.180 equals 0.280. 0.250 minus 0.09 equals 0.160. And then we were told that we had 0.180 of sulfur trioxide. So now let's calculate the mole fraction. Now the mole fraction is the number of moles of your individual gas you're looking at, which is sulfur trioxide. So the number of moles of our individual gas, which is sulfur trioxide, so 0.180 over the total moles at equilibrium. Okay, so we're going to do 0. No, it's of sulfur dioxide. So we want 0.280 over the total. So over 0.620. That's what you get if you add up all the equilibrium moles. So 0.280 divided by 0.620. What's that going to be? 0.3, 0.4-ish. That's our mole fraction. Again, you don't need to write the mole fraction. You're not getting marks for that. You're going to now multiply the mole fraction by the total pressure, because if you want to find the individual pressure of a gas, it's the mole fraction multiplied by the total pressure. So individual moles of a gas, to find if you do the mole fraction times the total pressure, you'll get the individual moles of a gas. So 0.52 times total pressure equals pressure of individual gas. And what do we get? 0.52 times 215, 0.452. So what are we looking at? 100 and, no, we're not even looking at that. 97. Let me whack it in the calculator and find out rather than guesswork T. 97.1. So you're going to round that up to 97.1 kPa. And there we go. Lovely bubbly. 3 sig, standard in chemistry. If you've not been told in the question to do it to a certain number of decimal places or significant figures, just use the standard 3 sig and you can't go wrong. A different mixture of sulfur dioxide and oxygen reaches equilibrium at a different temperature. The table below shows the partial pressures of the gases at equilibrium. SO2 is 1.67 times 10 to the 2, oxygen 1.02 times 10 to the 2, and sulfur trioxide 1.85 times 10 to the 2. Give an expression for the equilibrium constant Kp and calculate the value of the equilibrium constant for this reaction and give its units. Again, when looking at things like Kp, it's just the same as Kc with reactants divided by products. The only real difference, products over reactants. The only real difference is the shape of the brackets. So when you're doing Kp, we don't want to use square brackets like this. So I'm going to do it with square brackets first. So we've got 1.85 times 10 to the 2, because that's the product, sulfur trioxide. And we're going to do that over the top of the oxygen times the sulfur dioxide. So sulfur dioxide is 1.67 times 10 to the 2, and the oxygen is 1.02 times 10 to the 2. Now, if you write the Kp expression and you forget that you're not supposed to use square brackets, you're supposed to curve the brackets like this. See, I'm writing the expression up here. SO3, curved brackets, squared outside. And then we've got SO2 underneath, curved brackets with a square outside because its coefficient is 2 in the equation. And then we've got the oxygen. We don't need to put a number in front of the oxygen because we don't need to put a number outside the oxygen, because in the equation there was only 1 mole of oxygen. So if there's 2 moles of oxygen or 3 moles, I would have put a 2 or a 3 outside the brackets. But there was no coefficient in front of it in the equation, so we leave it like that. So get rid of the square brackets and use the curved brackets. Now the expression, when they ask you to write an expression, you don't have to write all the numbers in. They want the symbols, which I've done up the top there. So like SO3 to the power of 2 over SO2 to the 2 to the times oxygen. So now I'm going to replace that with the numbers, because we're going to calculate it. Okay. So what I need to do now is just calculate this up, and you're going to get like 1.2 times 10 to the minus 2, or I've made that look like divide, or you could write that as 0.0120. Doesn't matter, either one, it's up to you. So yeah, lovely jubbly. And that is in kPa. Now, if you want to know how to work out the units, you write the number of kPa's at the top. So it's to the power of 2. So there's 2 kPa's at the top. There's 3 kPa's at the bottom. So that means 2 of the ones at the top and 2 of the ones at the bottom are going to cancel out. But we still got that divide line. That line means divide, right? So we're going to divide the kPa We just got the 1 kPa, but we're going to put to the -1 because of the divide line. So it's kPa to the -1. Okay. And that is the unit. Lovely jubbly. Right, let's scroll down. Ba, 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 ba. What is the effect on the value of Kp if the pressure of this equilibrium mixture is increased at a constant temperature? So what is the effect on the value of Kp? So if we increase the equilibrium, if we increase the pressure, well, we're going to get an increase in yield because it's going to shift to the right hand side, right? It's going to shift the equilibrium if we increase the pressure to the side with the least gas molecules. However, this does not ask us about the yield, which it would increase. This is actually asking us about Kp. And just like concentration, changing pressure has no effect on Kp. So we would say the Kp would stay the same. And the reason is because it's a ratio. So when you change one, you change the other. Okay, getting into question 4. This question is about equilibrium. Part A, 1 mole of diester with a molecular formula C7H12O4 is added to 1 mole of water in the presence of a small amount of catalyst. The mixture is left to reach equilibrium at a constant temperature. We've got the equation C7H12O4 plus 2 water molecules goes to 2 ethanoic acid plus 2 diols. Oh, plus 1 diol molecule. At equilibrium, X moles of ethanoic acid are present in the mixture. Complete table 1 by deducing the amounts in terms of X of the diester, water, and the diol in the equilibrium mixture. So we're told there's X moles of ethanoic acid. So now we need to, express in terms of X, how many moles of diester, water, and diol will be present at equilibrium. So the ratio of our ethanoic acid to our diol is 2:1. So for every mole of X, you're going to have half X of diol. So you could write this as 0.5X, half X, or X divided by 2. So on the mark scheme, they go for X divided by 2, but you could really write half X or 0.5X. It'll be totally up to you. Now let's look at our moles of diester and water. So the ethanoic acid is in a 1:1 ratio with the water because they both have a 2 in front of them. So their coefficients are 2, so it's 1:1. This means that the amount of water left at equilibrium is going to be 1 minus X because there was 1 mole at the start. And if it breaks down in a ratio of 1:1 with the acid, the amount that will have broken down is X amount. So it's 1 minus X. But the ratio of the acid to the diester is 2:1. So it's going to be 1 take away X divided by 2. So only half the amount of X will come off of the acid. So you could write that as 1 minus 0.5X. And that's because it's in a 1:2 ratio with the acid, which has X moles. And there we go. 3 marks. Let's move on to the next part of the question. So next part of the question is deduce the structure of the diester. Now, the diester had the formula given to us in part A of the question, and the formula was like C7, what was it? H12O4. Let me have a quick look. Well, you've got to count it up and make sure that it equals the structural formula or the molecular formula that they gave us. And you can draw the skeletal formula in any format you want. It's totally cool. Let's have a look. C7H12O4. So that is the formula of the diester. So you've got the number of carbons, number of hydrogens and oxygens, and you just need to put them together, making sure it says diester. So you want 2 ester links, okay? make sure there's two ester links, and you can position the carbons and hydrogens on either side in any which way you see fit. And the examiner will give you the mark as long as it contains two ester links. And when you count up the number of hydrogens and the number of carbons, it works out. So if we do this, we just want to make sure there's 7 carbons. So look, I'm drawing them on in pink: 4, 5, 6, 7. Yep. And the hydrogens you don't need to show in the skeletal formula. So Bob's your uncle, Fanny's your aunt. All done. So on the mark scheme, it says you can draw any variation of that. Let me just show you another variation. So you could have like your ester link here, then we could have 1 carbon in between this time, and then let's do another ester link here. So just counting it up, making sure I'm not all over the place. And there we go. Let's add the double bond in there. So that's a different structure, but it still ends up being 7 Cs. Look, 6, 7. So as long as you've got 7 carbons and 2 ester links with the carbonyl bond and the oxygen with a single bond on either side, then you're sorted. A new equilibrium mixture of substances from part A is prepared at a different temperature. Got the exact same equation. The value of the equilibrium constant Kc is 0.161 at this temperature. Calculate the amount of water in moles in this new equilibrium mixture. Show you're working. So what we want to do here is just set our equation out. So we want to set out Kc, and remember that we're doing products over reactants. So we want to show the ethanoic acid. We're using square brackets because it's not Kp. We're not showing pressure, square brackets for concentration. And we're putting the coefficient top right outside the bracket. So for ethanoic acid, there's a 2. And then for this diol, there's nothing outside the brackets. And then we're going to do our diester C7H12O4, close the brackets, nothing on top of that. And then the water H2O, we're going to have a little 2 outside. So that's the expression. Now I need to just plug the numbers in and work it out. There's no rearrange. Oh no, there is rearranging for this one. We need to find out what the water is. So let's go through the rearrangement. So all you need to do now is plug your numbers in. So I want ethanoic acid at the top, 0.452. Oh God, that's so ugly. Let's redo that. So 0.452, close the brackets, put a 2 outside because the coefficient's 2 in the equation, times the diol, 0.273, over the top of 0.971, that's for the diester, times the water, and that equals 0.61. Oh, don't forget the water is to the power of 2 because there's 2 molecules of water on the reactant side, so I need to put a 2 outside the brackets for the water as well. Now, when rearranging slightly difficult equations like this, where you've got like 5 moving parts, I think to the old one I used to know from Key Stage 3, from year 7. Distance over time equals speed, or speed equals distance over time. So the equals, I've got 0.161. So that's like the speed. And then what's on top of the line is the distance, and underneath is the time. So I know I can rearrange it like that. If I want to find the total of the things underneath the divide line, I just need to do top of the divide line over 0.161, and that gives me 0.971 equals times H2O to the power of 2, like that, you see. So I just move the 0.161 underneath. Now what do I do? Well, I go, well, I want the H2O to the power of 2 on its own. So I'm going to divide both sides by 0.71. And as it's multiplying by 0.71 on the right, that's going to delete that over there. And I'm going to bring that 0.971 underneath next to the 0.161. So it's going to become 0.52 to the power of 2 times 0.273 over 0.61 times 0.71. And that is going to equal H2O to the power of 2, or H2O squared, and that is 0.357. I want to get rid of the little square sign, so I'm going to square root 0.357, and I'm going to get my final answer, 0.597. And there we go. We've calculated the amount in the mixture of water. Okay, let's get on to question 5. Which statement is not always correct for the reaction at equilibrium? So let's you got A, B, C, and D. If we look at D, this is true. The rate of the forward reaction is equal to the rate of the back reaction. That's always true at equilibrium. The next one, C, the equilibrium can be achieved from the starting products, true, and can be achieved from the reactants, true. It's reversible. So you can start with the products or the reactants and you'll reach equilibrium. The top one, the concentration of reactants and products are equal. Actually, normally they're not equal. So normally if you've got 60% products, 40% reactants, equilibrium, it will say 60% products, 40% reactants, but it's dynamic. Some of the products are breaking down, some of the reactants are forming products, but it just stays at that percentage. Okay, but it's very rare that it's going to be 50-50. Okay, question 6. Hydrogen gas can be made by reacting ethanol with steam in the presence of a catalyst. Give the expression for Kc for this equilibrium. So when you're writing the expression, you don't need to put numbers in, you just need to put the symbols in. And don't forget, Kc is equal to products over reactants. Um, and you just need to remember the shape of the brackets when it's Kc compared to when it's Kp. Most people do Kc in year 12 and you don't do Kp until year 13, but on physics and maths tutor, they blend both together into equilibrium. Okay, so I want to write my reactants. Notice I put a 2 outside the brackets and a 4. That's the coefficients. So they go out on the outside of the brackets. And then inside the brackets go the formulas and make sure the brackets are square because it represents concentration, which we use with Kc. Um, da, 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 da. We've got mole per decimeter. So we need to work out the unit. So, oh my days, I've got to write this out 6 times. Oh, sorry about the yawn, getting tired. So I've got to write out mole per decimeter 6 times. This is how I work out the units. You don't have to do it like this, it's long. So mole per decimeter 6 times on the top. And then how many mole per decimeters are at the bottom? Well, I've got 2 lots of square brackets, so concentration at the bottom. So I've got 2 mole per decimeter at the bottom. So I'm going to cancel out these bad boys. And that leaves me with 4 moles and 4 dm minus 3s. So that means it's mole to the 4, dm to the minus 12. And that's how we work out the units. Now, Part B, the table shows the amount of each substance in the equilibrium mixture in a container of a volume of 750 centimeter cubed. And what I'm going to do is put the equilibrium expression back on, get rid of that bit I did for working out the units. So I want the expression back on so we can see what we got to do. So, I need to take account this time. They don't always do this. Sometimes they just give you moles, but if they give you a volume, you must work out the concentration by dividing the moles by the volume. So we've been given moles and volume instead of concentrations. So I'm going to do 0.110 over 7.50. That needs to go into your calculator first and then squared. Make sure you use brackets in your calculator for this. Otherwise, you're going to make a mistake and flop the rest. But even if you write the arrangement out like I am now, 0.220 over 0.750, I know it's long, but it guarantees you a mark. So on the mark scheme, they're going to have the expression written out painstakingly like this. And it guarantees you a mark should you flop on your scientific calculator. So 0.0750 divided by 0.750. And then we have water, which is 0.156 over 0.750. So you just need to plug all of that into the calculator and you should get the answer. Now you can simplify this. So what you can do if you want is then go and do 0.110 divided by 0.750 and then write it out like that. Then 0.220 divided by 0.750, then write it out like that. So you get 0.146. And then if I do 0.220 divided by 0.750, I get like 0.93 to the 4. And then I get like 0.1 and then etc. Right. And then I get like 0.208, and then once you calculate all of that, you can then rewrite it. You can then rewrite it out again, and you can keep doing this if you don't trust your ability with your scientific calculator. But it's long; it's best to get to use that really well. And there we go. Or you can just whack it all in your calculator and put the answer straight down. And your final answer should be 7.66 times 10 to the minus 3. Bearing in mind, a lot of my working is roughly. Yeah, there we go. All right, let's move on to the final bit of this question. The pressure of the equilibrium mixture was increased by reducing the volume of the container at a constant temperature. Predict the effect of increasing the pressure on the equilibrium yield of hydrogen. Explain your answer. Predict the effect of increasing the pressure on the value of Kc. So essentially what we need to do is zing all the way back up and look at the amount of gas molecules on either side. So I've got 2G on the left and 4 gas molecules on the right. If we increase the pressure, which direction is it going to shift? Le Chatelier says it's going to shift to the left to reduce the number of gas molecules. Okay. So what's that going to do to the yield of hydrogen? Well, that means we're going to get less hydrogen because hydrogen's on the right and hydrogen is the product, which we talk about in the terms of yield. So the effect on the yield of hydrogen, it will decrease or it will reduce the yield of hydrogen. Explanation. The equilibrium position shifts to the left or to the backwards direction or the reverse direction because it has fewer gas molecules than the right hand side or the forwards reaction. And if you want, you can say the backwards or the left reaction forms 2 gas molecules, the forwards forms 4. So in order to follow Le Chatelier's principle and oppose the change, it will move to the side with the least gas molecules. Anywho, what effect does change in pressure have on Kc? No effect at all. Okay, same as the catalyst, there's no effect on Kc. Same as change in concentration, absolutely no effect on Kc. Sharing's caring, hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.